Hi everybody, this is Mr. Short. Today you can see we're going to be learning about molecular polarity. To start with, I want you to fill in these couple words right here: size, nonpolar, and polar. But also please understand, I'm not going to be assessing your understanding, your knowledge of dipole moments and net dipole moments this year. Okay, because of coronavirus, we have to move a little bit faster, so we're not going to be using this tip-to-tail method that's referenced in there. Down here, however, this concept about polarity is really important, so I'm going to highlight this. The term polarity indicates an unequal distribution of electrons, meaning if something is polar, then it has an unequal distribution of electrons. If it's nonpolar, then it has an equal or an even distribution of electrons. Typically, when we think about polarity, we think about two things, two perspectives concerning polarity. We already know this first concept. We can think about the polarity of an individual bond. So a bond is considered polar if the difference in electronegativity is greater than 0.5. So remember, you need the special table of electronegativity values. You take the bigger one, subtract the smaller one from it. If it's got a really small difference, less than 0.5, then it's a nonpolar bond, meaning that there's an equal distribution of electrons. But if the distribution is 0.5 or greater, then there's an unequal distribution of electrons. The electrons move closer to the atom with the higher electronegativity value, and that would be a polar bond. So we already know about point number one. Point number two, however, we can also think about the polarity of an overall molecule. And I can see that my definition here does reference net dipole moments, so I'm going to change this just a little tiny bit. We're going to say that a molecule is polar if it is asymmetric. Asymmetric. So I'm going to write this right over here. Polar if asymmetric. And I'm going to do something to emphasize that asymmetry means polarity, means that it's polar in just a minute. Okay, here's what I'd like you to do. I want you to take a minute and I want you to hit the pause button right here and draw Lewis structures for these 5 molecules. All right, so again, take a minute and hit the pause button. All right, I'm going to go ahead and draw these Lewis structures, but I want you to draw them first on your own. So remember, we start out with step number 1 of drawing Lewis structures. Step 2 is to draw the skeleton structure. I've already gone ahead and I've put the non-bonding electrons on the oxygen. Equals 16. I've been drawing these structures for a while, so I know this is going to form a nice straight line. And that we're going to have a pair of double bonds surrounding that central carbon. One other thing that you can see that I'm doing is I'm trying to space out the bonding and non-bonding electron domains as far apart from one another according to the acronym VESPER. So remember, VESPER stands for valence shell electron pair repulsion theory. And it means that we need to draw those bonds and non-bonding domains as far away from one another as possible. Here. Okay, because I know that ammonia, NH3, takes a pyramidal structure, I'm going to draw it like a pyramid, and you're going to see why that's important in just a minute. Right, CH4. Whoops. Carbon is our central atom, and it's flanked by each of the 4 hydrogens. "32 total electrons down here for this complicated molecule. Carbon is in the center. Each of the 3 chlorines are going to radiate from that central carbon. And you can see that we've got one lonely fluorine, which is going to be relevant in just a minute. Okay, there's our final structure for this. Now that we have proper Lewis structures drawn, according to the 5 steps for drawing Lewis structures, and they're drawn in the correct 3-dimensional orientation. Remember, if it's bent, we need to draw it bent, or if it's linear, we need to draw it in a straight line. So now that we've got proper Lewis structures drawn, what I'm going to do is I'm going to teach you an acronym that's going to help you to do a very simple analysis to figure out if the molecule is polar or nonpolar. So over here, I'm going to write the acronym SNAP. Here's what SNAP stands for. Symmetric is nonpolar, and asymmetric is polar. So remember, asymmetric is polar. That's the note that we wrote right up here. It's polar if it's asymmetric. So remember, when you're trying to figure out if an overall molecule is polar or nonpolar, you apply the acronym SNAP, symmetric, nonpolar, asymmetric, polar. So what does this mean? All right, I'm going to draw some lines of asymmetry for anything that is asymmetric. When you're analyzing for symmetry, you need to draw a vertical line straight down the middle and ask yourself if the left and the right are symmetric. You can see that the left of water and the right of water are perfectly symmetric with one another. But take a look. I also need to draw a horizontal line, and if the top and the bottom are different from one another, then overall it is asymmetric. So take a look. When I draw that line of asymmetry through there, the top is different from the bottom, therefore it's asymmetric. And since it's asymmetric, it's polar. Okay? Take a look. If I split it in half this way, the left and the right are the same. If I split it in half this way, the left and the right are the same. So this is symmetric, therefore it's nonpolar. Okay, draw your planes of symmetry or asymmetry. See how if I split it down the middle like this, the left and the right appear to be symmetric. But if I split it like this, the top is clearly very different than the bottom. Therefore, this is asymmetric, and it's polar. Okay. When I consider left, right, top, bottom, it's symmetric all around. Therefore, it's non-polar. All right, take a look at this one. If I split it like this, the top and the bottom look identical, symmetric. But if I split it basically like this, the left-hand side has fluorine and the right-hand side has chlorine. Therefore, this is asymmetric, and therefore it is polar. So remember, when you're thinking about whether the molecule is polar or nonpolar, you ask yourself, left, right, top, bottom, is it symmetric or asymmetric? If you can draw a plane of asymmetry, top to bottom in this case, or left to right in this case, then it's asymmetric and polar. Okay, let's ask the question why this even matters. Why is polarity important? Polarity is important because it affects physical properties, including solubility and states of matter. What do I mean by solubility? So two things are soluble, or one thing is soluble in another thing, if it can mix with that other thing. All right? So let's think about a simple saying right here to remember how solubility works. Up here we've got an acronym for how polarity works. Here is a simple saying for how solubility works. The saying is, like dissolves like. Okay, let's think about this. What this statement means is that polar dissolves polar. Okay, so for example, if we had water, which is polar, then ammonia, NH3, which is also polar, would be soluble in water. Okay, there are a lot of cleaners out there that have ammonia inside it. Ammonia is a really good cleaner. Okay, so this is soluble in this because both substances are polar. Okay, also, this statement means nonpolar dissolves nonpolar. Okay, so for example, we might expect that carbon dioxide would be soluble in methane, CH4, okay, because both of those are nonpolar. Okay, so both of these statements right here are true, but also it means that polar and nonpolar don't want to mix. Okay, polar and nonpolar don't mix. Think about something that you might attempt to mix in the kitchen that doesn't want to mix. You're maybe thinking about water, which is polar, and oil, which is nonpolar, because water and oil are two different polarities. Water is polar and oil is nonpolar. The two things don't want to mix. So I think the two big ideas that we've got right here are, once we've got a Lewis structure drawn in the correct orientation, we can attempt to draw lines of asymmetry through it, and if there is a line of asymmetry, then it's polar according to the acronym SNAP. Also, we can apply this statement down here, like dissolves like, to understand if two things will be soluble in one another or not soluble in one another. Remember, this is all based off of this term for polarity up here, where polarity means an unequal distribution of electrons. So what we mean by that statement in blue, as it relates to water, is that we've got a very electron-dense region right up here close to oxygen, but we do not have an electron-dense region down here close to hydrogen. Here, it's equally electron-dense all the way around when we consider the left side versus the right side. So since there is equal electron density, that's why this is nonpolar. Again, in this one, ammonia, NH3 right here, I can see that this is an electron-dense region right up here, and it's much more electron-dense here than it is down here at the bottom. Okay, so remember, the concept here is about molecular polarity. Anytime you're analyzing and asking the question, is a molecule polar or nonpolar, you apply the acronym SNAP. All right, thanks a lot, guys. See you soon.